Let's say you've got this huge pile of data, all sorted into neat little categories. And then, bam, a brand new, unknown piece of data shows up. How in the world do you figure out where it belongs? Well, that's the core challenge of classification. And today, we're going to look at one of the most intuitive ways to solve it.
So yeah, let's boil this down to a really simple question. When you're faced with something you've never seen before and it has no label on it, how do you make a good guess about what it is? It's a problem we solve all the time without even thinking about it.
And the answer, believe it or not, is super simple. You just look at its neighbors. You know that old saying, birds of a feather flock together? Well, that's pretty much the entire idea behind one of machine learning's most fundamental algorithms. We just assume that similar things tend to hang out close to each other.
Okay, so this whole company it keeps approach, it's got to have a formal name, right? So what is it called? And what exactly makes it so simple, but at the same time so powerful?
It's called K-nearest neighbors, or just KNN for short. Now, it's what's known as a non-parametric method, which is really just a fancy way of saying it doesn't make any assumptions about how your data is structured. The logic is incredibly straightforward. To figure out a new data point, you just find its K closest neighbors from your existing data. K is just a number you pick, and then you let them vote. Whichever category gets the most votes wins. Seriously, that's it.
Okay, that all sounds great on paper, but how does this really work when you've got a spreadsheet full of real data? How do we actually apply this idea of neighbors and voting in the real world?
All right, let's make this concrete. Imagine we've got data on a bunch of programmers. For each one, we know their location, their longitude and latitude, and we also know their favorite programming language. You know, you got your Python fans out in Seattle, the Java folks down in Austin. You get the picture.
So here's the puzzle. A new programmer signs up. We know exactly where they are on the map, but we have no idea what their favorite language is. So how do we use the data we already have to make a really good prediction?
Well, we follow a simple three-step dance. First, we pick a value for K. Let's just say we pick 3. Second, we calculate the physical distance from our new programmer to every single other programmer in our dataset to find the 3 absolute closest neighbors. And finally, we just look at what those 3 neighbors like. If 2 of them love Python and 1 is an R fan, well, Python gets the majority vote. And just like that, that's our prediction.
But wait a minute, that brings up a really important question. We keep throwing around this word closest, but what does that actually mean? How do you measure distance when your data isn't just a point on a map, but has multiple features, maybe on completely different scales? Right. This is where that simple idea of distance starts to get a little messy. To really see why, let's look at a totally new set of data comparing 3 people. Our goal here is to figure out whether person A or person C is closer to person B.
And this is where it gets kind of mind-bending. If we calculate the distance between them using their height in inches, it turns out person A is the closest neighbor to B. But if we just switch the units to centimeters, the math completely flips, and suddenly person C is closer. Nothing about the people actually changed, just our units, but we got a totally different answer.
So what's the big lesson here? It's that the scale of your data matters a lot. When one of your features, like height in centimeters, has a way bigger numerical range than another, like weight in pounds, it can totally overwhelm the distance calculation. It basically makes the smaller scale feature almost invisible. This is exactly why scaling your features is so important before you ever run KNN. Okay, so we've got a better handle on distance. But what happens if the neighbors just can't agree? You know, what if we pick K equals 4, and we end up with 2 votes for Python and 2 votes for Java? Now what?
Fortunately, there are some pretty simple, common-sense ways to handle this. For a simple two-way choice, you can usually avoid ties altogether just by picking an odd number for K, like 3, 5, or 7. But if a tie happens anyway, you can just have the algorithm pick a winner at random. Or another neat trick is to just reduce K by 1, so go from 4 to 3, and then check the vote again.
So far, KNN is looking pretty good. It's simple, it makes sense, but every algorithm has an Achilles heel, right? A major weakness we need to know about. And for KNN, oh boy, it's a big one. It's called the curse of dimensionality. And this quote right here, it gets right to the heart of the problem. You see, as you add more and more features or dimensions to your data, something really weird and counterintuitive starts to happen to the whole idea of distance.
Think about it like this. In a low-dimensional space, like a simple 2D chart, your nearest neighbor is usually way closer than some random point on the other side of the graph. The difference is obvious, but as you start piling on the dimensions, dozens or even hundreds of them, the distance to your nearest neighbor starts looking a whole lot like the distance to, well, to everybody else. That gap between closest and average just shrinks and shrinks.
And here's the kicker. The very foundation that KNN is built on, that idea that close points are similar points, it starts to fall apart. If every point in your dataset is roughly the same distance away from every other point, then being a nearest neighbor doesn't really mean anything special anymore.
All right, let's tie this all together. What are the big takeaways? First, KNN is super simple and easy to understand. Second, it's a lazy algorithm. There's no big training phase, it just uses the data as is. But on the downside, it's really sensitive to how your features are scaled, and its biggest weakness, its kryptonite, is that it really struggles as the number of features or dimensions grows.
And all of this leaves us with a really fascinating question to think about. If adding more and more features can actually make our model worse by making closeness meaningless, it forces us to ask, how do we figure out which features are the important signals and which ones are just noise? That's one of the biggest challenges in machine learning. Now, if you found this breakdown helpful, do me a favor and hit like and subscribe for more deep dives just like this one. Thanks for learning with me today.